Hey everyone, and welcome. Have you ever looked up at the stars and wondered how on earth we know what they're made of? Or, what's really in a simple glass of water? Well, it turns out that pretty much everything has a secret code, like its own unique chemical fingerprint. And today, we're going to learn how to read it. So let's get into it. Right, how do we actually crack these codes? I mean, whether we're talking about a star that's millions of light years away or just a single drop of water right here in front of us, the answer is actually the same. It's all about analyzing its light. And this kind of chemical detective work, it's got a pretty cool name. Yeah, it's called spectroscopy. And the best way to think about it is like a unique barcode of light that every single substance gives off. If we can just scan that barcode, bam, we know exactly what we're looking at. Today, we're going to dig into two totally different kinds of these light fingerprints, one for single atoms and a much more complicated one for when those atoms team up to form molecules. All right, so let's start with the basics, right? The most fundamental building block there is, the atom. When it comes to its light fingerprint, the atom is kind of like a single, simple, pure note. Just imagine a perfectly tuned bell. When you strike it, you don't get a whole complex melody, right? No, it just rings with one single, pure, clear note. Well, an atom is just like that. It can only give off light at a few very specific frequencies, or, well, colors. So here's how that works. It's actually a really simple two-step process. First, we zap the atom with a little bit of energy. That's like striking the bell. This gets an electron all excited, and it makes it jump to a higher energy level. But here's the thing, it can't stay up there. It almost immediately falls back down, and when it does, it has to release that extra energy as a little particle of light, a photon. And that photon will always have a very specific color. And that's it. That's the whole show for an atom. So because that whole process is so incredibly simple and so specific, the fingerprint it leaves behind is also super simple. It's called a sharp line spectrum. It honestly just looks like a barcode with a few really distinct, crisp lines. A simple bell makes a simple sound. A simple atom makes a simple spectrum. Makes sense, right? But what happens when those atoms join forces and form a molecule? Well, that's when our simple little note completely transforms into a rich, complex chord. This is where things get really interesting. So, okay, if an atom is just a simple bell, a molecule is way more like a full guitar. I mean, think about it. A guitar can do so much more than just ring one note. You can strum it, the strings can vibrate and hum, the whole body of the guitar can resonate, you can even spin it. It's just a much more complex instrument. And because of that, a molecule has what you could call a three-part harmony going on. It still has those electronic transitions, the electron jumping up and down, just like in the atom. That's our main note. But now it's got two completely new layers of complexity. The bonds holding the atoms together can actually stretch and bend. Those are the vibrational transitions. Think of that as the hum of the guitar strings. And on top of that, the entire molecule can spin around in space. Those are the rotational transitions, like the resonating spin of the guitar's body. And this idea connects perfectly with what our source material points out. It tells us that with molecules, you have to deal with all these new energy transitions. It's not just about electrons jumping anymore. You've got to account for all the vibrating and rotating that's unique to molecules. So what's the big takeaway here? With all three of these things happening at the exact same time, the electrons jumping, the bonds vibrating, the whole molecule rotating, the light that it gives off is no longer just a few simple, clean lines. No way. It's this rich, complex, messy mix of countless different signals. It's not a single note anymore. It's a full-blown chord. Okay, so let's do a direct comparison now. Let's put these two ideas right next to each other to make the difference totally crystal clear. We've got the atom's sharp lines on one side and the molecule's complex bands on the other. This table really just lays it all out perfectly. On one side, you've got atomic spectroscopy. Super simple, right? It's just atoms, only electronic transitions, and the result is that sharp line spectrum. But then you look at molecular spectroscopy, and it's the whole shebang. You're dealing with molecules, you've got electronic, vibrational, and rotational transitions all at once. And you get this complex band spectrum where all the lines are so packed together, they kind of just blur into wide bands. It really is the difference between hearing a single note and hearing an entire symphony. So, a simple note versus a complex chord. You might be thinking, okay, cool, but why does this actually matter so much? Well, this fundamental difference is everything. It's how we read the story of the entire universe. This is exactly what allows scientists to be so incredibly precise.
When they're looking out into space and they see a simple, sharp line spectrum, they know, without a doubt, they're looking at a pure element, like the neon gas in a glowing sign. But when they see a broad, messy, complex band spectrum, they know they're looking at a molecule, like the water vapor in a distant planet's atmosphere. It's the difference between identifying one instrument and identifying an entire orchestra.
So I'm going to leave you with this final thought. We've talked about a single molecule being like a chord, but a single drop of water, that has trillions upon trillions of molecules, all vibrating, rotating, and interacting with each other constantly. So if every single one of those has its own unique spectral chord, just try to imagine the unbelievable symphony that's constantly playing out, totally unheard, in every single drop of water. Pretty amazing to think about.